This is going to be 100-1. We've entered into a new unit, exponential and logarithmic functions, and so we're going to introduce these types of functions. And so we're going to examine the graphs and properties of exponential functions. So today we're just going to be focusing on those exponential functions. Now, these types of functions, these exponential functions, they're actually special to our society. And believe it or not, out of all the other functions that we've examined, exponential functions actually impact our society the most. You're actually going to see more real-life applications with these exponential and logarithmic functions than any other function before. Now, up to this point, we've talked about functions that had exponents, right? I'm using this term, exponential functions, but they are similar to like x to the third or x to the 5/7. But we haven't actually talked about instances where my exponent itself is the variable, like a to the x power, right? That's different. So what we're going to be doing is we're going to be focusing on those instances where our exponent is actually going to be the variable. Now, this is what a basic exponential function looks like, and in this instance, f of x to the 2x. This is the most basic. Now, the way that I graphed this, or at least modeled this, was I took my -3, plugged that in to my function, so I got 2 to the -3, that's 1 over 8, plotted the point. And you go through and you create your list of points, and here I go. I have the model of what that basic function looks like. Now, there's a few features that we should take a look at here, like what about my end behavior? Well, x can go to -infinity, and x can go to +infinity. Now notice, as my x is going to -infinity, my x values are getting smaller and smaller, it seems like it's approaching this value 0. And that's exactly what's happening, is that my y is approaching 0. And if my value, my x is going to +infinity, it's going to go up forever. And so my y is actually going to go up forever. So my y is going to go up to +infinity. And so these are some of the unique features that you're actually going to see with a lot of these exponential functions, is it seems like my x in one instance will approach an asymptote, and then my y in the other instance is going to go up to infinity. And so we can define it, and we can say that a function in the form f of x equals b to the x power, or b is a fixed number, or b is greater than 0, is called a base b exponential function. So this is an example of our exponential function, and this is the definition of what our exponential function is. Now, what if b is between 0 and 1? What happens if I have this 1/2 to the x power? Well, there's going to be an issue here. And what I need to do is, if my definition, we said that it has to be b is greater than 1, I have to manipulate my equation here to where b is -1, greater than 1. And so what if I bring the 2 to the top here? Well, now I'm going to get 2 to the -1, and that's going to be the x power, and now I can multiply those two exponents together, and I get 2 to the -x. Well, this 2 to the -x it's very similar to my previous function, except now that I have this negative in front of my x, I now have a reflection across the y-axis. And so if I reflect it, notice here's my original, this gets reflected over here, this part gets reflected over here. And that's exactly what happened here. This got reflected over to here, this got reflected over here, and so this is my 2 to the -x. So just know that if I have this 1/2 to the x power, that's informal, and I want to qualify it or change it to where my base b is greater than -1. You just need to recognize that there's going to be some sort of reflection going on there, okay, when we graph it. Now, here are all the properties of my exponential functions. My domain is always -infinity to +infinity, so there are no domain restrictions. Now, my y, or my range, has a restriction. So just know that my range is never going to be -infinity to +infinity. The point 0, 1 on the graph, this is going to be your fixed starting point in terms of, if you remember, we can shift things horizontally, we can shift things vertically, we can do all of that stuff. And so because we can do all of that, if I have this image based upon this idea of being able to shift my function left and right, up and down, we should be able to have a starting point in which I need to do that. And so 0, 1 on my graph is going to be that starting point. And always y equals 0 is a horizontal asymptote. So I'm always going to have a horizontal asymptote here at y equals 0. F is a one-to-one continuous function, and it's smooth. So there's no gaps, there's no jumps. Now remember, if b is greater than 1, always increasing, and then we kind of defined our domain, or our end behavior. And then if b is between 0 and 1, it's going in the opposite direction here because there's that reflection over the y-axis, and my end behavior also changes as well. So just remember those instances. So this first one, what if I wanted to graph 2 to the x minus 2? Well, there's two ways we can do this. We could plot points. I can take -1, plug it in, 0, plug it in, 1, plug it in, 2, plug it in, etc., and I can get my list of points here. That's always a way or a means for us to do that. But what if I wanted to graph it in terms of my shifts, right? We have a horizontal shift. We have a vertical shift that's possible. And so in this instance, I only have a horizontal shift, right? We have to do the opposite here. So my h is 2, so it's going to shift over 2 spaces. So if we want to take a look at that, we model the original, right? My starting point was here at 0, 1, and then everything shifted over 2 spaces. And so that's another way of modeling it. So I could graph this and just draw the line that's right here, right? We can just draw that line that's there through that box. Or if we wanted to look at it in terms of shifting, drawing a sketch, you start at 0, 1, shift everything over, and that's going to be your image. Now I'm going to clean that up so you guys can take a look at that better. Let's look at another one. This time I now have that this is a vertical shift. This graph is going to shift down 4. Remember, we can still plot points. If I still wanted to plug in -2 and -1, etc., it's still going to give me those values to be able to do that. But now if I wanted to take a look at it in terms of, my standard form function, this is where it started, right here at 0, 1, but everything shifted down 4 spaces. Now notice what also shifted. My horizontal asymptote originally was y equals 0, but that shifted down 4 as well. So we need to pay attention to that. Whenever we have a vertical shift, your horizontal asymptote is also shifting with your graph. So my advice is just to kind of understand that you can do both. Okay, you can pick points, plot them to be able to get it, but it's much easier to just draw a sketch. Starts here, there's my sketch, and then draw the transformation from whatever the sketch is. So in this case, everything shifted down 4 spaces, and so you'd be able to draw everything being shifted down 4 spaces. Let's look at example number 3. Let's actually kind of apply this to a real-life model. It says the value of a car can be modeled by this function here, v of x equals 25 to the 4/5 x, where x is greater than or equal to 0 is the age of the years in car, and v of x is the value in thousands of dollars. So find and interpret v of 0. Well, v of 0, that's where if it's x is the age, right? So that means that this is like time that's elapsing. So this is the value of a car when it's new. So 25, 4 over 5 to the x, and it says in thousands of dollars. So if I plug in 0, I'm going to get 25, 4 over 5 to the 0 power, which is 25 times 1, which is 25,000. So it's $25,000. That's what it's going to worth, but this is when it's worth brand new. So that's what it means. If my age is 0, this is what it's going to be brand new. And you're actually going to see these types of models, depreciation in terms of what a car is worth actually follows an exponential model. And so you can actually sit there and take a look at these exponential models of these cars and be able to determine, this is buying a used car. This is the best time to buy the used car because I'm going to save the most money in the long run. Example number 2, or part 2, it says sketch the graph. So for us to be able to sketch this, it might help us to kind of create a table. If we wanted to do transformations, kind of doesn't tell us a whole lot of information, but we could do it through transformations if we wanted to. If I plug in x is 0, we said that was 25. If x is 1, well, this is going to be 25 times 4/5. That's going to be 5 times 4, so that's going to be 20. if x is 2, and then so you can sit there, and I would probably start plotting some of these in my calculator. If x is 2, 25, 16 over 25, so that's going to be 16. And so if we can't do that, let's maybe do like 5. Let's get ahead of ourselves. So 25, 4 over 5 to the 5th power. So entering that in our calculator, you're going to get a nice decimal. It's 8.192. And so drawing our graph of 0, here's 1, here's 2, here's 3, here's 4, here's 5. And so say 5, 10, 15, 20, 25. So here's where it started at. After 1 year, it lost 20% of its value. Yikes. After 2 years, right, it's only worth $16,000. I just want to know, 16 out of 25, after just 2 years of owning the car, it lost 36% its value. It's a third of its value in 2 years. Why buy a new car? That's so much. So 20, so it's about right there. That's about 16 right there. And then at 5, we said it was about 8.2, so that's about right there. And so as we can see, it's probably, it might be dipping even lower like that. So it's probably following that type of model right there. And it looks like it's approaching 0 there. So then actually step 3 says find and interpret the horizontal asymptote of the graph that you found in 2. Well, you know, that is my horizontal asymptote right there. And so believe it or not, for part 3, my horizontal asymptote, all that means is eventually if it's approaching 0, it means eventually my car is going to be worthless. Eventually my car will be worth $0. So eventually the car is going to be worth $0. So just know that eventually your car turns into trash. So might be a good idea in this instance, you know, to purchase a new car and sit there, or a used car, and be able to sit there and determine when do you think you get the best value in buying your used car. And so I even did that for my own Impala. You know, I bought that thing used, and it was only 2 years old. Used 2 years old, had 1,000 miles on it, and I actually ended up saving. I mean, you know, even like looking at it as a percentage, let's see, how much did I pay for it after it was brand new? So I actually paid only 62% of what it was actually worth when it was brand new. Almost 63%, 62 to 63%. So I saved about 37% just by buying it used. 2 years old, only had 1,000 miles on it. So that's just kind of something to kind of think about there. Now, in conclusion, what concepts were discussed today? We took a look and introduced exponential functions, the graphs and how they look like. We kind of talked about some of these real-world concepts and how they could be applied. Now, just remember, I need you guys to focus on the image, what it looks like, the form. Those are the important things, and even the characteristics of those. Like if you were to think, like, what's the domain? Right? Maybe even post that in the YouTube comment. What's the domain of all exponential functions? What's the range of a exponential function that doesn't have any transformations? Things like that. We need to know what those are. And then what I also want you guys to comment is, how are the transformational shifts similar to other functions? So I want you guys to compare it. We've done these types of transformations with other functions before. How are these going to be similar? And then I also want you guys to research other applications for exponential functions and share your findings in the comments. So this does conclude our lesson. As usual, if you have any other questions, please leave them in the comments.